Welcome to another RDWorks Learning Lab. Today I've escaped to my workshop. I'm working less for the boss and I'm enjoying life for myself. Now, over the past couple of months I've gradually been acquiring bits and pieces to do this particular work, and I've done one or two experiments along the way, some fairly abysmal failures, and gradually working towards an element of success. Now, following on from my success with wood burning, or not, and with 3D engraving, where I managed to get rid of the burning process, so that started to raise a few questions about just what's going on when we manage to do sort of engraving on paper with dots. Yeah, it must be the brown around the edge of the dot that's giving me the colour, not the centre, where there is actually probably a very small hole. I started doing some experiments with card, and I quickly realised that really I'm not going to be able to push the boundaries until I change the material. I realised quite a long time ago from a little bit of experimental work that I did that you could get some quite high resolution pictures on anodized aluminium. I happen to have an anodized section of aluminium on which I was able to just experiment on the face of the aluminium. And if we look at the results that I was getting, compare that with my finger, you'll see that, it's quite a lot of detail in there, and I can't see many dots. That's because this picture was done at 1,000 dots per inch. I didn't understand why, but what I found was that if you go too high with your power, you burn right through the anodize to the raw aluminium that's underneath, and that's what the dark grey is. I think before we start this, what I really ought to do is try and explain, for those of you that have not come across anodized aluminium before, just what the process is. Now, I got some ordinary aluminium offcuts from a colleague of mine. These are just guillotined sort of squares, but they're nothing special. Anodizing is an interesting process because, first of all, aluminium, silver aluminium like this, raw aluminium in any state, is extremely reflective, about 99% or more reflective to infrared radiation. So it becomes technically a mirror, and the last thing you really want to do is to fire a laser beam at it. It's a bit dangerous, which is why I covered up the base plate, the aluminium base plate, in my machine with a piece of mild steel. The first part of the anodizing process is to take plain aluminium and put it through an electroplating type of process where there is a conversion of the surface into an aluminium oxide. Now, it's the first stage of anodizing that this piece of aluminium has gone through. It's not finished. Now, aluminium oxide's a product that you probably will recognise. It's a very, very hard wearing product. You've seen it in sandpaper. You will have seen it in grinding wheels. If you could imagine little grains of salt laying on the surface, they're just a few microns thick, and it's a coating which is basically porous, as I said, just like salt. There are little spaces between the grains of salt. And then what happens is, you either, if you want it this colour, silvery, you put a sealing process on top of it. It then seals up all the pores and produces a nice finished glossy aluminium anodized product. That's a two-stage process. Now, if you wish, you can make it a three-stage process, so that before you actually put the final sealing coat on, you drop the product into a dye, and you infuse those gaps between the oxide crystals with a dye. Now, in that particular instance, it was gold. In this particular instance, it's black. I mean, there's a huge range of dyes that you can use to produce a coloured aluminium anodized product. They then go back and seal the surface. So then it becomes a coloured finished anodized product. So I suspect that this is a much thicker anodizing on here. Whereas this might be 1 or 2 microns thick, this could be as much as maybe 5, 8, even 10 microns thick. So my quest really was to try and find out, why can I get such high resolution pictures on aluminium. So I started off with the standard approach. Let's run some burn tests on the surface. That didn't really help me a great deal. I didn't burn through to the base material underneath. Now, you'll notice what's actually happened with those samples. They are white. And you'll notice what's happened with that one. That's white as well. Once there is an oxide layer on the top of this raw aluminium, it no longer acts like a mirror. The oxide is actually extremely receptive to infrared radiation. It takes the light in and converts it to heat at the surface. And so you get tremendous heating effect just at the surface. And what we're really doing there to produce that white effect, we're evaporating the dye that's between the crystals on the surface. And what we're left with is aluminium oxide, which is a white product. But as you can see, if it's thin enough, you can burn through it, although it's extremely resistant to burning. My initial thoughts were that this is basically a very delicate process, and it requires a very small amount of energy to evaporate the dye out of the material. So that's why I carried out these tests, to try and find out just what sorts of powers and speed I could expect. So the next problem to try and determine was what resolution was I going to try for, because with card, soft materials, wood, we've got a very well proven formula that works. But it works because we're allowing a certain amount of time for individual pixels to form. Although we appear to have lots of different shades in there, in reality what we've got is dots that are closer and closer together and dots that are further and further apart to produce shades of grey in the brain through the eye. So it's a trick. So using my little test, which is not as big as this, I've just done this to show you, where we've got individual pixels, pixels with spaces between them, and lines, various size lines, so that we can determine whether or not we should be able to see those when we do tests. Can we work out what size dots we've got? Various speeds, various feeds, various resolutions. And we'll take a look at some of those results shortly under the microscope. But before I bore you with those, and if I do those towards the end, you can just jump to the end. The golden rule is high frequency impact engraving. Let's work in the pre-ionization zone for the tube, right down at the bottom, low power, which seemed to work very successfully for this. 1,000 dots per inch, and I was working at 11%, 12%, 15%, burnt a hole through it. So 15% was too much. So I did a couple of experiments, and I was working at 300 dots per inch. I thought, let's go for it. And look, what looks like a half reasonable picture. That was done with 20% power, 20% power, and 300 dots per inch. But in reality, when you get close to it, it's not. So it's a bit like me. The further you stand back, the better I look. Now that was using a 1.5 inch lens, and again, I tried a few more times, different parameters. That one I aborted because I could see it was not going to be any good. This one, well, it's dark, and as you'll see from my dot tests that we'll talk about later on, there was absolutely no reason to suggest that I was going to get very good results by doing what I've done. I took a leap of faith based on this work, where I was using 1,000 dots per inch and 200 millimeters a second. Out of fresh air, I decided, hey, let's go for 400 dots per inch, 240 millimeters a second, and 50% power. Close up, you can see the scan lines, but you can't see the dots. Yeah, I said 50% power, but that's not 50% power straight. That's using something called special mode. Now, we talked about special mode a long time ago when we talked about this thing called facula. Okay, now I've now set the machine into special mode, and I've done a trace for you of power which is the red line, and the switching on and off, which is the blue line. Now, it's purely a coincidence, but as you can see, there is my pattern. That top line are the continuous lines, and they match up with this pattern. Under normal circumstances, what you'd see is you'd see the signal switching on here, off because it's blank, then back on, off, on, off, on, off. But with special mode, it's broken up into 20,000 hertz signals. And what I've done, I've set the facula to 50%. So that means the signal is only on for 50% of the time. I've divided the power effectively by 2. But in reality, it's a lot less than that, because I don't think the actual physics of the machine through the power supply can respond that quickly. But that's what the machine is trying to do. It's trying to break these continuous signals into smaller pieces. When we get to this next set of lines, we can see the middle row of dots. Well, if we take a look at those, depending on how they arrive, these are single dots. Sometimes we've got signals which break up. The dot is on long enough to produce like 2 or 3 little signals, and then at other times there's not enough for it to only do 1 pulse, 2 pulses, 1.5, 1, 2, 1, 3. You know, we're getting a strange pattern along here, an aliasing pattern basically, where the pulsing does not coincide with the pixels. We're likely to get varying colours on these pixels because we haven't got exactly the same signal on each one. Varying powers across all of these dots at this resolution, which is 300 dots per inch. Now, I haven't got the single dots to match up because I've expanded the scale so that you can basically see what's happening. Look, we've got a dot, a dot, a dot, a dot and a bit. That dot is broken into 2, that dot is broken into 2, a dot, something funny going on there. You know, we've got some randomness taking place along here. So we've got, again, inconsistency in the power signal for single dots. But the whole point of it is we're breaking up the dots into smaller little power intervals. And that gives us the opportunity to do as I've just demonstrated to you. I put 40 or 50% power into these dots. Now, I just don't know how much further I can push this, because this is 600 pixels per inch. I'm running it at 240 millimeters a second and 40% power. Now, it's not really 40% power because I'm running this on special mode. If we take a look at what's happening to the ammeter, it looks as though I'm on something like about 8 watts, 6 or 8 watts at the most, but I actually know the tube is trying to output over 60 watts. That's one of the dangers of using this special mode. You must not take any notice of the ammeter because it's averaging out very, very high frequency pulses, and it's just giving you totally wrong information. Very good news here for those guys with very high powered lasers, because using this special mode you can back the power right off, and there's a very, very high chance that you will be able to do this sort of work as well. So we'll go and analyse what's happening to these dots now under the microscope. Now, I'm purposely starting off this job with a 2-inch focal length lens because I know that most of your machines will be supplied with a 2-inch lens, and see whether we can get up to 1,000 dots per inch. I'm going to spend a bit of time on this picture explaining what things are, and then we'll skip through the other pictures quite quickly with just a few cursory comments. That centre line of pixels along there is basically a pixel, 3 gaps and a pixel. So in essence we're talking about a centre distance of 4 pixels, and each pixel
at 300 dots per inch is around about 0.08. 4/8's 32, 0.34, that's the dimension between those pixel centers. They're just about touching each other, so those pixels must be 0.3 to 0.34 diameter. And the same applies to the top row, so we can see that top row of pixels there. They're even maybe slightly bigger, but they vary between maybe up to 0.4 diameter. Technically they should be 0.08 apart, but because they're so big, they're just overlapping each other. Now, something of interest is this center row of pixels. You'll see that some of them have got little black dots in the middle of them. Now, I've mused on this for a little while, and I think that those little black dots are basically power points. They're penetration points that go right through the anodizing. And then what we've got a little white halo on the outside. Now, the other thing to note is the inconsistency of the quality of dots along that center line, and even more so along the bottom line. Now, if you remember, when we looked at the oscilloscope pictures, we found that there was a strange aliasing effect where some dots were complete, some dots were half spikes, some dots were quarter spikes, and that's what you're seeing here. Different density according to the power that's been administered to those dots. We'll take a look at what happens to these top and bottom line thicknesses as we change the power from 60 down to 50 and then down to 40%. Now, as we skip through these 50%, you'll see that the line at the top and the bottom are getting a little bit weaker. You've still got some strength in the middle line, but as we pass to 40%, you definitely see a big change. The top and bottom lines are definitely thinner, and the center line has nearly disappeared. So I've used exactly the same power in both special mode and common mode so that you can see the difference in the line thickness between the two modes. And that's 40%. And then 50%. And then 60%. Now, just to give the 1.5 inch lens a fair crack of the whip, what I did was to wind the power right down to 10% and take it up through to 16% to check what the line looked like during high frequency impact engraving or pre-ionization. Well, now I've changed to a 2-inch meniscus lens, and at 40% the results are looking pretty good. Once we get to 50%, they're going up a little bit in thickness, but we're getting some consistency on the middle line. At 60%, well, yeah, the lines are getting a little bit thicker, but they are becoming more uniform. And then just to show you the comparison again between special mode and common mode, we've got 60%, which then at 50%, yeah, there's a big difference between them. And at 40%, well, yeah, there's almost good on the common mode. Now, the surprising thing is that the 2-inch lens is actually very good, probably better than the 1.5 inch lens. Now, finally switching back to common mode with 20% power, which is above the pre-ionization zone, the 2-inch focal length lens actually looked pretty good. And of all the choices, I might have plumped for that particular one. But we have got a result for that. And to be honest, it's not very good.
So just for the record, this is about 80 millimeters by about 115 millimeters wide. And this took 14 minutes to produce. This was done a resolution of 400 dots per inch, a speed of 240 millimeters a second, and power of 50% and 50%. 50% would be normally about 55 watts after the lens. So there's quite a hideous amount of power here, which has not destroyed the picture. It hasn't burnt through to dark greys. It's a pretty reasonable quality picture. Now, under normal circumstances, you'd think this was very good. As I said, this was done with special mode. This was exactly the same program run at 40% power in common mode, and as you can see, literally it's just burnt all the colour out of it. So my next attempt was 600 dots per inch. Now these were done with a 2-inch meniscus lens, and they were running at 240 millimeters a second. This one was done at 50% again, and it took 21 minutes, nearly 22 minutes to produce this. Now I don't know whether it's possible to see the comparison there. If you look at places like here, you can see the lining, the scan lines, whereas you really can't see that many scan lines here. There's an extra degree of crispness here at round about at 600 dots per inch. There's also a change in the colour, as you can see. This colour here is slightly brown, whereas this colour here is much more a crisper white. Okay, so it still didn't fail at 600 dots per inch, 240 millimeters a second. What is going on? So if we take the special mode off and run it in common mode at 20% power, this is what we get. A badly washed out image. Again, for comparison, they're both done at 400 millimeters a second. This one here was done at 40-40 power, and this one here was done at 50-50 power. There is actually a cleaner picture at 40-40 power than there is at 50-50. Now here we have our finished product at 1000 dots per inch. This is 240 millimeters a second, 40% power, and special mode with a 2-inch meniscus lens. Now this is actually staggering. 40-40-400. This is a 40-40-1000. Now there is a difference between them when you look at them really, really closely, but not a huge difference. The amount of time that this took was probably close on an hour. So although this one looks like a slightly cleaner picture, I don't think it's worth the extra half an hour to produce this picture as opposed to this one, which happens in about 14 minutes. Staggering results, but why?
This is the 400 pixels per inch picture. The most obvious thing there is that we can see the scan lines. There are gaps between the scan lines. So we set the scan lines to 063. Interesting question is, what do they show up as? Well, that's rather interesting, isn't it? Because the scan interval is about 0.12 of a millimetre, and yet I programmed it as 0.08. Now you'll notice we've got some of that frog spawn again. Let's just see what size those are. The last time we saw them, they were about 0.1. They were about 0.2, weren't they? They're about 0.18, I would think. Now we can see the vertical grain there on the black, so that has not been affected. But there are places where it's been partially interfered with. The good thing is these look like they should be single pixels. They're big, but they're single pixels. And it could well be that some of these pixels are a little bit grey because we haven't leached out all of the dye, because each pixel is not the same power as it should be, if you remember from the oscilloscope pictures. So that could be having an effect on this as well. But every effect that we're seeing is a positive effect, because I keep just panning around here because I want you to get a feel for what 400 pixels per inch looks like Let's just have a look for comparison finally at the two eyes. There is the left eye as we look at it, and there's the right eye as we look at it. Keep those images in your brain and we'll go and look at the similar things, the left and the right eye, for the 1000 pixel per inch. So there's the left eye as we look at it. Not as many granulations in there, are there? Let's have a look at what the line width is this time, because we can see a very clear line across there. Now it's about 0.1. So there is definitely a difference in the line thickness. We're running at the same speed, we're running at the same power. The only thing that's different is the resolution. Well, we see a lot more joined up granulation. We don't see many actual lines. And the dots that we see, the white dots that we see, let's just see if we can work out what size they are. Again, they look to be about 0.1. So this machine is really beginning to amaze me now, because it can pick up 0.1 at 240 millimeters a second. I mean, there is a definite difference here between 400 and 1000 pixels per inch. I'm not saying that this is actually producing 1000 pixels per inch, but something in the mechanism is giving us a very high quality picture here. And I think the clue is in something like, these strings here, where we can see we've got lots and lots of dots. That must be the high frequency facula coming in, the pulsing. So let's just see, at 1000 pixels per inch and 240 millimeters a second, just what the numbers are, because basically what I'm trying to work out is how many of these special mode pulses per pixel. And it turns out that there are 2 of them, so every pixel gets 2 little pulses. The really puzzling thing is that I programmed this with a 0.0254, let's just say 0.02 pitch per line. Now I can't see any hint of that. We're seeing approximately 0.1, 5 times the size of the pitch that I programmed into that machine. At the moment I'm getting more questions than answers. I'm getting nothing that makes any logical sense, except I'm getting a fantastic picture as an end result. And that frustrates me because I want to know why. Now my machine has got a claimed resolution of 0.01, in which case it should easily do the 0.025 or 0.03 that I'm asking for this particular interval. 1 division equals 0.1 millimeter, and that is the width of those scan lines as far as I can see. I mean, I'm just looking for clues on whiskers, for example. On the other side, again, look, we can see all the lines. They're 0.1 wide. Well, there we are. It's doing exactly what we expect it to do. Pixel, pixel, pixel. Block of 2 pixels, 2 pixels, lots of pixels, 2, a block of pixels and a great big block of pixels there, all in one go. But that block of pixels there is broken up into lots of little pieces. So this scanning across the picture is doing exactly the same as we did across the pattern. Despite a claimed resolution of 0.01, the display is only showing 0.1 of a millimeter. So let's just see, we've got a 600 resolution program in here. Let's see how far it moves, and then we can work out approximately how much per scan.
1, 2, 3, 4, 5, 6, 7, 8, 9, 95, 96, 98, 99, 100.
So over 100 scans, the machine moved 4.2 millimeters, giving us 0.042 millimeters per scan. And the increment that I set for a 600 dpi picture was 0.0423. So give or take the last tenth of a micron, the machine appears to be very accurate. So why is my scan increment, according to the lines, only 0.1? What is going on? I mean, I should be able to see about 3 lines in 0.1 of a millimetre. Well, here we have a 400 resolution picture. And if we start counting from the 3, we've got basically 1, 2, 3, 4, 5, 6, 7, 8. And here we've got 1000 pixels per inch. This is not the same granulation. So we're definitely not talking about anything to do with the material itself. But we're going to try and count down, see if we can work out how many scan lines we've got there between 0 and 1. It's a very difficult task because, let's just see if we can get the focus any better. When you start looking at it in detail, it's almost impossible to work out where the scan lines are. You can see them, but you can't count them. Well, we've got a few black lines here that we're able to use to guide us. 1, 2, 3, 4, 5, 6, 7, 8, 9. Puzzling, because that doesn't make sense. 2.5 times the resolution, but only 1 line extra. At 1000 lines per inch, 25.4 divided by 1000, 0.0254. So how many of those would we expect to see in a millimetre? 39.37. So we'd expect to see 40 lines in a millimetre there. But we know the machine is actually moving at approximately the correct resolution. You see, we look at places like just here, oops, just there, and you can see there are 2 lines very close together. There wouldn't be 40 of those in a millimetre though. 0.1 pitch, maybe 0.08 pitch.
We're going to do something close to vandalism. I've got some acetone here, and I'm just going to remove any hint of grease and oil from the top of that slide. That's not too bad, is it? But what I'm just about to do now is almost a criminal activity, except this piece of little kit is only about 10 or 12 pounds off eBay. So if it gets ruined, it's not exactly a fortune. But one of the things that I can't trust is the movement of this slide. I know what it tells me on the display, and we've checked that the overall motion is correct. But of course that information is coming back from the stepper encoder. It's not coming back from the physics of the beam itself. So what I've now got to do is to measure what the step size is for the beam. I'm going to do that with my digital caliper. So I've got some very high bond strength tape, double-sided tape on the back there, and I'm going to stick it to the slide. Okay, well, I've put the speed down to 140 millimeters a second now, just so that it gives me a longer sweep time and allows the readings to settle on there. So let's give this a try, shall we? So that's going up by 0.04, isn't it? 60, 64, 68, 72. So there's a carryover from time to time. And here we go. I can assure you that no verniers were harmed in the making of this video.
Well, I've had to go back and do a 1000 dot per inch test, and these are the results of that test. You can't even see the middle line of dots. They just don't show up. What we've got the single dots at the bottom, which are multiple hits. Obviously they would normally be 0.02 apart, so you'd expect to see 4 of those dots for every division shown on the screen there. They look very much like 0.1 steps. That's what they look like. But we've done the calculations, and we know that for 1000 dots per inch there are supposedly 2 hits for every dot, and there should be 4 dots per division shown on that screen. Well, that top row of dots there is anything from 0.15 to 0.2 diameter, which is 10 times bigger than the pixel size. So that just is even more puzzling as to why this system works. Now, the only reason that I can begin to think of is that with this size dot, we're obviously not getting the resolution that we expect, but we're getting a very good quality picture, because what's not happening is we are not over burning because we're doing multiple burns. The first or second burn seems to be taking the colour out of the aluminium oxide. It's evaporating the dye. But unlike with wood or any other organic material, a second and third and fourth and fifth burn doesn't make it any deeper, any darker, because it's white already, and the material, the aluminium oxide, is resisting the heat and it's not disappearing. So it doesn't really matter how many times you overburn it, it will always look like this. So I can only think that by overpainting the same spot or overburning the same spot many times only reinforces its real general colour. We know that the machine is responding correctly to the step instructions. So we know that that picture is composed of lines that are 0.0254 apart, even though the blobbiness of the picture seems to create a different impression. I'm still not clearly understanding how the quality of this picture is being transferred down onto this aluminium oxide. All I can say is that this special mode is doing a superb job, and the possibility of reaching 1000 dots per inch is a bit of a dream, but the reality of it is 1000 dots per inch gives a very good quality picture, even though I'm absolutely convinced what we're seeing is not 1000 dots per inch, but it is a superb quality picture. Well, I hope that hasn't been too confusing. Thank you for your time, and we'll see you in the next session.